Thank you. In designing Python, Guido had specific uses for tuples and lists, and in particular did not want tuples to become simply read-only lists. And in the early days of Python, this was maybe a little easier to accept because tuples and lists were the only two types that were kind of analogous to each other. But since then, we've had sets and we've had bytes. And in both these cases, both mutable and immutable forms were added to the language. I thought it'd be interesting to take a look at the missing types on this table. What would they be? How would they behave? Would they even be useful? Let's start with the numbers, int and float. What would a mutable int and float look like? In trying to conceptualize this, I was picturing an object that held one of these numbers, but otherwise behaved like that number. And I thought, how useful is that really? How often do you have just one number that you want to modify? Normally you have several, meaning you're probably using a class, meaning you don't need a mutable number at all. So I'm not going to spend much time on this. Okay, a mutable string though, there could be more meat on this bone. First, let's give it a name. And let's look to bytes for some inspiration here. So one element of a byte is a byte, of course, and a mutable bytes is a byte array. So let's apply this onto strings, where each element is a char, a chr, as per the built-in function. Therefore, let's call a mutable string a char array. Makes sense, right? The implementation for this has a couple interesting corner cases, most notably indexing and slicing. Of course, both these operations on a string return a string. Does that mean it should return string on char array as well? Or should it actually return a char array? Here again, we can look to bytes. If we look at bytes and byte array, we can see that slicing returns an object of the same type. And this is true for tuples and lists and strings, and it should be true for char array as well. You should get back an object of the same type. Indexing a byte, oddly, returns an integer. At least I was confused at first, but it kind of makes sense. In all of these cases, both strings and bytes, we're getting back an immutable object that represents one of the elements. And in the case of char array, that immutable object is a string of length 1. We don't have mutable strings, then how do we wind up with mutable bytes? Well, in researching this discussion, I was actually interested to find that the initial design was to have just a single mutable byte type. But what was found was that people wanted to use bytes as, for example, keys in dictionaries. And so the design was changed in the very early days of Python 3 to have these two types that we have today. Now, if we had this char array, would it even be useful? The embedded developer in me says, yes, of course. You want to minimize your memory copies. You want to minimize your allocations. So yeah, this would be great at that. Frankly, in the context of Python, though, I had trouble coming up with a compelling argument here. Because once you learn join or string IO, it's pretty easy to efficiently create a string dynamically. Further, while char array would be excellent at replacing individual characters in a string, normally you're not doing that. Normally you're adding and removing characters, meaning all the remaining characters in a string have to shift back and forth in order to line up the indices. This even got me wondering, I wonder if in hindsight, byte array was a good idea. Has it actually been useful? I'd be interested in your feedback here. Okay, let's now set that aside and look to immutable dicts. And to give this a name, well, sets have frozen sets. Therefore, let's call an immutable dict a frozendict. In fact, exactly this was proposed in a Python enhancement proposal, which was rejected, but out of that, we got the mapping proxy type. This is a useful type, and I'd like to even see a sequence proxy type added, but it doesn't go far enough, and let me explain why. So let's take this very simple bit of code. We create a source object, we take some state from it, and we use that to create a recipient object. Inside both of these objects, it's storing some state as a dictionary that cannot change. In the case of source, because it exposes this state, it has to make a copy each time it does so. It doesn't know who's on the receiving end of this function call and what they might do to that object. The only safe thing it can do is make a copy. The recipient must also make a copy, because once again, it's being given this dictionary, but that doesn't know who else has access to it and what they might do. So it has to call dict again. That's 2 copies in this case, whereas we can see in this very simple example, neither is required. Nobody is going to modify this dictionary. We can improve this situation a bit today by using that mapping proxy type. And here's how it works. It is a read-only view into a dictionary. For the source, this makes perfect sense. It can now return this proxy object and trust that no matter who has access to this, they're not going to be able to modify the underlying dictionary through that proxy. So that gets rid of one of the copies. On the recipient end, though, it has no such guarantees. Because even though it's a read-only view, the underlying dictionary can still be modified. Read-only does not mean immutable. So in this case, it must still make a copy. This is where I think frozendict would be a benefit. On the source side, the state could be stored directly as a frozendict. And then the neat thing here is source could just return a reference to that object directly. It doesn't have to create a copy. It doesn't even have to create a proxy object. On the recipient end, if it receives a frozendict, it knows it can use that object directly. Nobody's going to change it. Otherwise, it could just make a copy again as it has to anyway. Even this bit of code can be simplified down to just simply calling frozendict. This is similar to how tuple works today. If you take the tuple constructor and you call it an object, but that object is already a tuple, you get back that object immediately. No copying is made. Frozendict could behave the same way. So this is my argument for why a frozendict could be a useful addition to the language, because it gives assurances to both the source and recipient of a dictionary that it will not change. With frozendict rejected, well, who was able to sneak frozenset in? So once again, the initial intention was to just have a single mutable set type. But the people doing graphing algorithms wanted to be able to represent sets of sets. Those inner sets had to be hashable and therefore immutable. So this wouldn't fly. So we got both the set and frozen set types. Implementing a frozendict is going to be pretty straightforward. Just hack off a few methods from a regular dict. One method that's gained, though, is the hash. How would you hash a frozendict? Well, you could take the keys and pass it through tuples hash algorithm and use that. That doesn't work because that hash very much depends on the order of items, and of course, keys are unordered. Well, okay, frozenset has a hash algorithm, and it's already set up to deal with unordered data. Let's just use that. We're getting closer, but 2 frozendicts with different values should compute to different hashes. Further, and more importantly, the hash function should fail if you try to call it on a frozendict that has mutable values. Just as today, if you have a tuple containing a mutable value, that will fail. So the final solution, as proposed in the PEP, is to take the items, both the key and the value from the frozendict, and use that to compute the hash. And there you have it, car array and frozendict. And no matter if your tuples contain heterogeneous or homogeneous data, I hope you've enjoyed this trip through the missing types.